Okay, now let's look at this virus reproduction problem. So in a simplified model of COVID-19 virus evolution, we assume that initially there's only one virus. This virus have two possibilities, either die with a probability of 0.1, or successfully evolve split into two new viruses with probability of 0.9, initiating a new generation of the virus. And each virus ensuring generation, for example, for second generation, have the same potential outcome of either dying or splitting into two new viruses independently, following the same probability as the initial virus. The question is asking we to determine the probability distribution for a number of viruses in the third generation. So basically, this is asking us to find out the PMF for number of viruses after third generations. So let's see how to solve this problem. We can solve this problem by using the probability tree. Initially, for the first generation, we only have one viruses. We have the probability of 0.9 to evolve to the next generation, which will produce into two viruses. And then it will have 0.1 probability, it will die. Hence, in the third generation, it will have 0 viruses. And then we looking at this particular path here. Once we have two viruses in the second generation, then we will need to analyze what is the outcome for the third generation. The first part is that both these two viruses successfully survived and split into two new viruses. So the probability of this is nothing but 0.9 times 0.9, because each virus, whether they can evolve or not, is independent. And each virus, they have a 0.9 probability it will evolve. So this is the first scenario. The second scenario is that one of these viruses will die, another virus will evolve. Hence, we can choose two. Either virus 1 is survive or virus 2 is survive. Hence, we have two scenarios, which is to choose one. And then the probability of one virus die and one virus is survive 0.1 times 0.9. And for this particular outcome, we will end up in two viruses. The third scenario is that both viruses will die. For this particular case, will be 0.1 times 0.1. Both viruses will die. It will lead to the 0 virus in the third generation. So here actually is quite clear. So probably I just draw some boundary here. So this is first generation. This is the second generation. And then this is the third generation. So we are interested in the probability distribution of the number of viruses in third generation. So we can easily see from this tree that there are three possible number of viruses in third generation, which is 4 viruses, 2 viruses, 0 viruses. And then we have already listed down the probability for each pass. Hence, we can just populate the PMA for this particular random variable. Let's call X denote the number of viruses at the third generation. Then we can easily populate this PMF table as the answer for this particular problems. So first, when X equal to 0, basically there are two possible scenarios. The first scenario is that the first generation virus is die immediately, which have 0.1 probability. The second scenario is that the first generation virus is evolved, but the second generation viruses are all die. So this is the probability of 0.9 times the probability of 0.1, 0.1. Hence is this. This is from here and here. So this is for the scenario where the X equal to 0. So for X equal to 2, similarly, the first generation virus is evolved, and then one of the two viruses survive in the second generation. Hence is 0.9 times 0.9 times 0.1 times 2, which is corresponding to here. Then actually we can just using 1 minus this and this to get the probability of X equal to 4. Or we can also using the probability to calculate 0.9 for the first generation to survive, 0.9, 0.9 for both second generation viruses are survive. Hence here is this. and here is from here. Then we can calculate the probability of the third generation of 4 viruses. So for this kind of problem, if you can draw this probability tree, and then it's quite trivial for you to come out the solution for this particular PMF tables. So that's the solution for this question.